In this video, we're going to do some modeling with exponential functions. And I first want to point out scenarios in which exponential functions are appropriate or provide useful models. The first would be the case where you have a situation where something is doubling, like a population is doubling, or tripling, or quadrupling, etc., every so many hours or years or something like that. When you see that, that's a hallmark sign of exponential growth. Another situation, and this is common in finances, and in population actually, where you have 3% or 5%, 6%, 0.86% or whatever, etc., growth every so many years. Or, so this arises a lot both in finance and in population growth statistics. To give you an idea as to why this occurs, I'll go ahead and illustrate what happens when you double every few years. But for this video, we're going to assume that when we have population growth, that it can be modeled with an exponential function. All right, so let me show you why, for example, if you double every few years, that leads to exponential growth. So for example, population doubling every 3 years. Let's say the initial, so this is the population at a time t in years, and p naught is the initial population. So what happens after 3 years? Well, the population after 3 years is going to be, well, it doubles every 3 years, right? So it's going to be twice what it was initially. And initially it was p naught. Okay, then after 6 years, you're looking at double that, right? So it's twice this, so twice 2 p naught, and that can be written as 2 squared p naught, and there's the beginning of the exponential growth. Now, the population at 9 years, well, it's twice what it was there because it doubled again. So it's twice 2 squared p naught, and now we're looking at 2 cubed p naught. And you can guess what's going to happen, right? At p, the population at 12 years is going to be not 2 to the third, but 2 to the fourth p naught. And so generally, in this case, you have the population at t number of years. To get this number, all you do is you take the number of years and you divide by 3. So it's 2 raised to the time divided by 3 times p naught. And so my point is that we had a population doubling every 3 years, and that led to an exponential function. So 2 to the t over 3 times p naught, where p naught's a constant, that's an exponential function. Okay, so that's why those two scenarios I described on the previous page lead to exponential growth. Okay, let's do some problems that you're likely to see in your class. So, before that, sorry. Generally, we can use any positive number for the base of the exponential function. Like in the previous example, we ended up with 2 raised to the t over 3, but you can choose any positive number you want because you can convert back and forth between two different exponential functions. We choose the number e generally, and those reasons have to do with calculus, where we do something called differentiating, and it just so happens that e to the something is the easiest function to differentiate in calculus. So our general form that we're going to be used for modeling is this. N, where n might be the number of people or the number of whatever, the population, the amount at some time t is this. N sub 0, that's the initial population when the time is 0, times e is about 2.71828, raised to the RT, okay, and R is the relative growth rate. So basically, when we do exponential modeling, the first thing we're going to do is to say, okay, the equation is going to have this form, and our job is to find, it could be a few different things. Usually you have to find R, or maybe you have to find the initial population or the population at a certain time. So, but this is the general model, okay? N naught, where that's the initial population times e raised to the RT. Okay, let's see that model in action now. Okay, so a bacteria culture, and like I mentioned, populations, we're going to assume they grow exponentially. So a bacteria culture starts with 8,200 bacteria. After 2 hours, we're told the population is 10,000. Okay, so it jumped up quite a bit in 2 hours. Find a function that models the number of bacteria n of t after t hours. That's part A. Part B, find the number of bacteria after 3 hours. Part C, after how many hours will the number of bacteria double? Okay, so for part A, we're going to assume, like I mentioned a moment ago, that the function we're looking for is n naught e raised to the RT. Now the question you have to ask yourself is, do you have any of these things initially? Do you know what n naught is? You do, right? Because you're told the bacteria culture starts with 8,200 bacteria. That's the starting population. That's what n naught represents. So we have n of t is equal to 8,200 e to the RT. Okay, and now we have to get r. And once we have this and that, we'll have a complete function because e is a constant and t is the independent variable. Okay, so r is some constant. It's the relative growth rate. And we're going to find that using the other information we're given, which is that after 2 hours, the population is 10,000. That is the value of the population is 10,000 when t is what? When t is 2. So let's write that in. That 10,000 is equal to 8,200 e to the 2r, because the time is 2 and we're multiplying by r. Now we want to solve this equation for r, and then once we do that, we're going to substitute back here to have our function. So the first thing we're going to do is divide both sides by 8,200. And then we can simplify, so canceling, and let's see, 2 zeros and 2 zeros, so we end up with, let's see, 100, make that 100, divided by 82 is equal to, what's on the right-hand side? E to the 2r, okay? And then we have to solve this equation for r. Do you remember how to solve an exponential equation? Well, whenever what you're looking for is in the exponent, you take the log of both sides to bring it down. Now, because the base is e, we're going to use the natural log. So the natural log of 100 divided by 82 is equal to the natural log of e to the 2r. And then what happens is this is just 2r by the cancellation property. So the natural log of 100 divided by 82 is equal to just 2r. That's why we did it. And then we're going to divide both sides by 2, so we have this. R is, if you take this and divide by 2, that's the same as having 1/2 times the natural log of 100 over 82. So r is about equal to, we're going to need a calculator for this. And when you calculate it, we end up getting, let's see, what do we end up getting for this problem? 0.0992. That's our value for r. Okay, and that means that we can take that value of r and substitute it right there, and that'll give us our function. Okay, so our function, that is our answer to part A, is this. N of t is equal to 8,200, the starting population, times e raised to rt. So r is this, 0.0992 t. Okay, that's a 0 right there. And that's our answer for part A. Okay, now part B, what does part B ask us to do? It says find the number of bacteria after 3 years. Now once you have this function, all you have to do is plug in 3 to get the, so this function gives you the number of bacteria at any number of years. So if I want to know the number of bacteria at 3 years, I'm just going to plug in 3 for t. That's the whole point of this function. Okay, let's do that now. So we're going to need to do that on another page. So I'm going to plug in 3 for t. Let's go ahead and do that. So I'm right here. So I'm plugging in 3, and I get n of 3 is equal to 8,200 times e to the 0.0992 times 3. And then our calculator, we're going to evaluate that right-hand side. And n of 3 is about equal to, what do we end up getting? 11,042 when we do that on our calculator. Okay, so what it means is that after 3 hours, the bacteria population has grown to about 11,042 bacteria. Okay, in part C, ask us how long does it take the population to double? Now remember, the population started at 8,200. And if it doubles, right, what does it get to? Well, it gets to 16,400. So what we want to know is how long does it take to get to 16,400? Let's write that here. We want to know, when the population is 16,400, what's the time? That's what we're doing. So e to the 0.0992 t. That is, we're solving this equation for t. I plugged in twice the initial population on the left-hand side. And so I divide both sides by 8,200. And of course, on the left-hand side, those cancel, and this divided by that is going to be 2. That's the whole point. So double, right? This is double that. 2 is equal to e to the 0.0992 t. Now we're going to take the natural log of both sides, just like before. And we get the natural log of 2 is equal to 0.0992 t. Divide both sides by that, 0.0992. 0.992. And what do we get? We get, let's do that up here, we get that t is about equal to, on our calculator, about 6.99 hours. Okay, that is about 7 hours. So it takes this bacteria population about 7 hours to double. Okay, so let's go ahead and do another example now with something that's a little more, not realistic, but something that is sort of close to home, and we'll see that you don't need a large growth rate to have significant results. So here's the example. A population has a relative growth rate of 0.86% per year. Think about that. That's pretty low, right? It seems like it's saying, hey, less than 1% a year, 1% of the current population. That's how it seems like it's growing slowly, right? You're only getting less than 1% of the population growth every year. Let's see what happens. If the current population is 40 million, in how many years will the population be 50 million? Okay, so now when you have a percent growth rate, you can take your function, let's write n of t is equal to n naught e to the rt, and r is that is the relative growth rate. Okay, so the percentage growth of the population per year, that's what r is. So in this case, we can just go ahead and substitute that in right there. So we get n of t is equal to n naught e to the, okay, r. Now you have to convert it to a decimal. It's 0.0086 t. So, and of course, what's our initial population? Well, we're starting off with 40 and we're asking when does it get to 50? So we want to know when this is 50 if you're starting at 40. Let's write that, and this will be in millions. So 50 is equal to 40 e to the 0.0086 t, and that's the equation we have to solve. So we'll divide both sides by 40. And we get 5/4 on the left-hand side. So we have 5/4 is equal to e to the 0.0086 t. We're going to solve by taking the natural log of both sides. So the natural log of 5/4 is equal to, and when you take the natural log of this, the natural log and the exponential cancel, and you get just 0.0086 t. Dividing now both sides by 0.0086 to get t, right? That's what we're looking for. Those cancel, and we get this. T is about equal to 25.95 years. Okay, that is about 26 years. What's the meaning of this? Well, it's saying that if you start at 40 million, you get to 50 million in about 26 years, assuming that what seems like a relatively low growth rate. Now, these are statistics that I found for California. That is, the current population of California is about 40 million. And the question is when will it get to about 50 million, assuming a growth rate of 0.86%? And the answer is in about 26 years. Think about that. In 26 years, which isn't that long, the population is going to grow by 25%, right? It's going to go from 40 million to 50 million. That's huge. So the point is that what seems like a relatively low growth rate, if you're talking a large population, that is significant growth, even though the rate is deceptively low. And the same thing goes true with your investment. For example, if you invest, and you're making 2 or 3% a year, that's a very large rate of growth, right? And over time, it grows exponentially, and so you end up with quite a large number in not that long of a time. And that's why people say, compound growth is so important, because your investment grows exponentially. Okay, until next time.